Imagine that we are now sat in a classroom and that you are told that you have to dictate a melody that will be played in C major, best notated in treble clef, in the 2/4 time, and is 2 measures long. You'll get a brief tonal setup on the piano, and then hear the melody after hearing a rhythmic clave setup kind of like this. And this is where I will play a musical example, but it never plays through QuickTime, so I won't bother doing that here. You might be able to write it down right away, but if you're like most oral skills students without absolute pitch, this is a non-trivial task, and you might find yourself between the figurative step 1 and 2 of the owl from before. Well, here's the melody. It's a cadential figure from Schubert's octet in D major. Now, I'm sure that there are many ways in which this could have been dictated, but I want to use this excerpt to demonstrate how my model would complete this task. So if we take this short melodic excerpt and run it through instantiation of Marcus Pierce's computational model of auditory cognition, also known as idiom, we'd get some output that would give us measures of probability for each musical event that would occur, in this case, these 8 notes. From that probability measure, we can then calculate how much information content is associated with each event. But all you really need to know is that unexpected events have high information content, like this F moving down to the A, and expected musical events, like our leading tone resolving to the tonic prior to stepwise motion, have low information content. If we interpret these information content measures as proxies for memory, we could imagine listening to the same some melodic material, like this one here, and having the notes sort of quickly fill up a buffer of memory, or your working memory capacity, with every passing note. More unexpected notes would fill up the bin quicker, and vice versa. This might be hard to imagine as a chart, so I've made this nice little GIF of how this might happen over the course of time. Again, we see more unexpected notes, like the F down to the A, filling up the buffer of memory faster than the B going to the C. The beauty of conceptualizing melodic memory in this way is that then you can start accommodating for possible differences in the memory buffer of people by just adjusting that parameter in the model as reflected here in the dashed lines. On one side, we maybe have someone who has a bigger bin than the other side, so the right side being bigger. Conceptualizing how fast notes fill up the bin using information content also has benefits, in that we can then imagine different people are going to be better or worse at expecting musical events, which we then can also reflect with the model. For example, in the middle here, we might be modeling someone with a high working memory capacity and a decent ability to expect notes deriving from more training and exposure as predicted by the statistical learning hypothesis, and this difference is reflected in the prior knowledge module. This conceptualization also gets around the problem that come in trying to follow in the shoes of George Miller, referring to the ability to remember 7 plus or minus 2 items. Applying this item concept directly with music is riddled with problems that stems from music's sequential and hierarchical nature. So the idea of mapping notes to items is now replaced with our ability to chunk musical material baked right into the model's ontological assumptions. If we then accept that this is the way that this is how we can represent melodic information in memory, we can then talk about this as a larger process. We can go back to our example from before and look at what happens when the model actually hears some Schubert. So according to the model, the melody is first fed into the selective attention module, where we have set the prior knowledge and working memory capacity parameters ahead of time. In this toy example, I've set working memory capacity limits to about 17 bits, as marked by the dashed line. In the prior knowledge, and the prior knowledge is essentially a database of musical patterns that are either explicitly or implicitly known, that also needs to be set ahead of time as well. As soon as the model starts, it adds a 1 to the difficulty counter and the first attempt of the search, and you get your first attempt of the search pattern. So the notes would be read into the model with their associated information content until the cumulative information content passes the limit of working memory capacity. This would signify that the listener has enough information in their memory buffer, but hopefully not too much, because in addition to retaining this information, they also need to be able to manipulate it. In my model, there is no figure it out module, as I said before, but rather a string of notes, or quite literally a string in the program, which will be cross-referenced with the prior knowledge, aka our long-term memory. If what is in the buffer of memory finds a match because of the threshold set earlier, then we have our aha moment, and the melody gets notated. If, on the other hand, we've taken too much information and can't find a match, the model would truncate a bit of the melodic string, thus breaking it down into smaller pieces, and this pattern would happen recursively. In starting the search again with a smaller musical unit in the buffer without finding a match, we would then add another counter to the difficulty counter. This is an example of the model working harder because of more iterations of the model. The process, this process would happen either until a match is found that is explicitly understood, or it just can't find anything and would move on. Now at this point, there are hundreds of things that might go wrong during the dictation, but because the assumptions of this model are based in plausible psychological phenomena, the model actually captures some of this.